Okay, well, I think we're going to go ahead and get started. We have a few more people who may be joining us. My name is Theresa Gunn. I'm the project manager for the on-site wastewater program. And we're pleased to bring you the first in a series of trainings and meetings. Hope you all received our email. We do have 2 other meetings coming up this month and next month. So on July 26th, we're going to walk through the changes to the rule that recently went into effect in June and highlight those minor technical updates and give you an update on where we are in what we're calling phase 2 of rebuilding the on-site wastewater program. Then we also do have another training in August 16th, and that's with Ray Morgan, who will be sharing with us how to operate and maintain your septic system. I've seen that presentation, it looks really good, so be on watch out for that one as well. Couple of housekeeping things. You are muted and you will stay muted throughout the presentation. We are recording the first part of this presentation. If you have any questions, you will see your pop-up menu. If you just see a red arrow, and that it will hide and expand your control panel. And if you go down, you'll see a gray bar that says questions. And if you type your questions into the question panel, then Kevin will be able to see those and respond to them. So do not put them in chat, put them in the question window. And if you have any concerns about audio or anything else during the session, feel free to type a comment in that questions window. All right, so now I'm going to go ahead and introduce Kevin Sherman, who's an engineer as well as a PhD. He's with Septitech right now, but he is a former regulator in the state of Florida. And he has graciously volunteered his time to help us work on phase 2, and as well as share this presentation that he's been given across the country. And so I thought it was good information to start thinking about high strength waste here in Arizona. So with that, Kevin, I'm going to go offline or go off video and let you take it away.
Okay, I'm also going to go off video because I don't want to run out of bandwidth halfway through this presentation. Okay, so hello everybody. My name is Kevin Sherman. I'm a professional engineer licensed in the 17 states shown on this slide. If you're listening to this presentation in any of the states listed, you are hearing the voice of a licensed professional engineer. If you're listening in a state or Canadian province not listed on the bottom of this slide or anywhere else in the world, you're hearing the voice of an informed layperson. I work as Director of Engineering and Regulatory Affairs for Septitech, Inc. in Lewiston, Maine, and I am passionate about high-strength wastewater. So let me begin this presentation with a warning. If toxins are present in the wastewater that you are trying to treat, and it's in significant concentrations, what I'm about to teach you here today simply will not work. So I'm going to limit this talk to discussions of microbially available wastewaters.
Kevin, did we lose you?
No, I'm here, but it advanced before we got started, and now it doesn't want to advance. So
oh, okay.
take a look at this.
We have to click on the screen that your presentation's showing from. Because sometimes if you use your mouse to click off the screen, you have to go back to the screen and click.
There we go. Get off the screen, yeah. So the first question is, what is high-strength wastewater? And in a nutshell, it's wastewater that exceeds our accepted concentrations for domestic wastewater for at least one strength measure. Now, these parameters are biochemical, oxygen demand, or carbonaceous biochemical oxygen demand, is shown here. Total suspended solids, something called FOG, which stands for fats, oils, and grease, and finally, total nitrogen. Now, it may be in the future that other parameters are added to this list, but let's next state, so we're exceeding the accepted concentrations, but I haven't told you what those concentrations are. So let's see what domestic wastewater is thought to contain for these 4 parameters. So influent, what's going into a septic tank, would have a CBOD around 300 milligrams per liter. TSS might be a little bit higher than that, around 350. Total nitrogen, 70 milligrams per liter, but in areas with lots of water-saving fixtures, it might be higher than that. And FOG, 75 milligrams per liter coming into a tank. Now, this is not in the Arizona code, but don't feel left out. It's not in most on-site wastewater codes. So FOG is definitely something to be on the lookout for. And typical domestic sewage will have all 4 parameters close to or below these stated concentrations. But if any one or more parameters are substantially above this concentration, that result by itself classifies the waste as high-strength wastewater. So there are many different kinds of high-strength wastewater, depending upon which parameter is out of domestic wastewater level strength. So let's go on and get this going. There it is. Okay. So here are some examples of high-strength wastewater. And these facilities expect to exceed just the one parameter that I'm talking about. So a veterinary clinic would have TSS above the 350, and all the other parameters would be below their respective standards, but just that one thing is enough to make a veterinary clinic high-strength waste for TSS. Interstate highway rest areas will very likely exceed the concentration for total nitrogen due to urine addition as people drive back and forth on the highways. Food service establishments are sort of the poster child of high-strength wastes, but there are many different types of food service establishments. So, for example, the solution that we might come up with to deal with high-strength waste from a bakery would not be appropriate for a drive-in hamburger and shake place. So there's specifics within high-strength waste for food service establishments. We'll talk about that later in this talk. Most food service establishments are characterized by having high levels of both biochemical oxygen demand and fats, oils, and grease. Now, this list is by no means complete. There are many other examples than these, and they range from everything from retirement communities to factories. So these are examples of high-strength wastewater. A question I get a lot, and might as well answer it now, is can you get high-strength waste from a home? And the answer is yes, you certainly can, based on activities inside the home. It's not typical that home wastewater will be high strength, but through acts of omission and commission, and also just some positive reasons, you can get high strength waste out of a home. So here's a error of commission. If you're taking in several neighbors' laundry and doing that in your house, you're going to have high strength waste similar to what a laundromat would have. If you're using your kitchen as a catering commissary, that would make that wastewater much like a food service establishment. If you extensively misuse the garbage disposal, you'll probably have high levels of fats, oils, and grease, possibly BOD as well. And then disposing greasy residues down the sink also would create fog issues for the home. And then a positive thing is the best cook in the neighborhood. If Mary is making braciole and I can smell it, very easily. When she is, I'm going to return one of the tools I borrow from her husband on a regular basis so that I can at least get a taste of this delicious dish. So next, we want to explain how the laboratory measures these strength parameters. And I want to demystify these procedures so you'll be able to understand them and not be intimidated by them. I kind of feel like they use very fancy names for things with the idea of like a secret handshake. So I'm going to bust that that myth right now. So first one is biochemical oxygen demand. So biochemical oxygen demand is a measure of oxygen used to break down organic material and other chemicals. The test begins by measuring the dissolved oxygen in a sample. The container is sealed airtight and then placed in an incubator in the dark at 68 degrees Fahrenheit, which is room temperature. No light is allowed in the cabinet during the 5-day incubation period. After 5 days, the container is unsealed and the dissolved oxygen is remeasured in that same sample. Say the initial dissolved oxygen was 5.85 milligrams per liter at the start, and after 5 days, it's remeasured, and now it's 3.45 milligrams per liter. The amount of oxygen removed from the sample, 2.4 milligrams per liter, is the demand microorganisms living and growing in the sample placed on the concentration of dissolved oxygen in the water inside that container. Because microbes reproduce quickly, populations can double in number in 20 minutes to an hour. In 5 days, which is 120 hours, one microorganism can grow to a population of over 1 million to as many as quadrillions. The term CBOD means the 5-day carbonaceous biochemical oxygen demand. And the way that we get that is that we take a BOD sample and add 1 drop of acetone into the 1 liter sample. It instantly kills all the nitrogen-related microbes. So to demystify that, I want you to think of BOD and CBOD as the tastiness of the sample to aerobic microbes. Now, if the sample is not tasty, one of 2 things could be happening. It could be a very thin gruel, doesn't have growth factors in it, or second option is it could have a whole bunch of those growth factors in it, but it's also toxic. So you could feed somebody a salad and steak with hemlock juice in the salad, and they aren't going to finish that meal. The next parameter is total suspended solids. And for a total suspended solids measurement, a water sample is filtered through a pre-weighed standard glass fiber filter by vacuum. Let's say you weigh a new dry glass fiber filter, and a microscopic photo of what that looks like is in the lower right-hand corner. You use a very accurate Mettler scale to make this determination. When you do this, the filter initially weighs 2.56837 grams. You have it to that number of digits. Now take a liter of sample water and place it in a funnel above the filter, and then turn on the vacuum pump, and by vacuum, it'll quickly pull the water through the filter. Once that has happened, that surface would be peppered with different pieces of small material that help to clog it. But we have to take that filter, we have to remove it, dry it, bone dry, no moisture in it whatsoever, and then measure it again. And however that weight has increased by, that is TSS. So the recorded weight increase per liter of sample. The fully dried filter now weighs 2.63473 grams. So the TSS is 66 milligrams per liter. So think of TSS as the murkiness of the liquid. This is a photo courtesy of my friend Denise Jantrania from Texas A&M University. and it shows to the left a sample from a septic tank. In the middle is a sample of the recirculating sand filter where it's in the mixing zone, where fresh effluent from the filter and older effluent is mixed together. And finally, the one on the right is the discharge effluent from the recirculating sand filter. With each step, the murkiness of the liquid got substantially better. Another parameter, fats, oils, and grease. So fats, oils, and grease are similar to each other in that they are all lighter than water. We use something called a separatory funnel, which is shown over here in the photograph to the right. And a sample is mixed with a liquid called hexane and allowed to settle. Now, hexane and fog float together, the top layer of this Italian salad mix. Open the stopcock and let the heavier liquid drain out. Place the upper layer in a pre-weighed container. Under a fume hood, the hexane evaporates. Hexane is a material that isn't a supposed or assumed carcinogen, it's a known carcinogen. So the closest I want you to hexane is looking at this picture. But the weight will increase, and what is increased there is the fats, oils, and grease, because that pre-weighed container now weighs a little bit more, and that is the fog. So fog is a measure of floatable substances. A properly functioning grease interceptor is important to controlling fog, and we'll get into this topic in earnest later in the presentation. Next parameter is nitrogen, and total nitrogen is the sum of total Kegdal nitrogen, TKN, plus nitrate, NO3, and nitrite, NO2. Nitrogen is a remarkable element. It binds with other nitrogen atoms to form N2 gas, diatomic nitrogen gas. And there are literally billions of tons of this nearly inert gas in our atmosphere today. It makes up 78% of the air that we breathe. Other forms of nitrogen, however, are explosive. For example, there's something called TNT, which stands for trinitrotoluene, and that, you know, if you knock into it, you could make it explode. So this slide comes from the textbook Wastewater Engineering. The author is George Voneglis, but the historic title of the book is Metcalf and Eddy. It shows that BOD is a little more complicated than it might seem at first glance. Yes, microbes consume carbon. They're called heterotrophs, and they consume some of the oxygen in a sample during a BOD test. But they're not alone. A second very different group of microbes called nitrifiers also exert a separate NBOD, or nitrogenous biochemical oxygen demand, on the sample. Nitrifying bacteria include species from the following genera: Nitrosomonas, Nitrobacter, Nitrospira, and others. These bacteria are all what are called chemoautotrophic. That's a pretty fancy name, isn't it? Well, chemo means chemical, auto means self, and troph translates to feeding. So a chemoautotroph uses chemicals to feed itself. Another example of an autotroph is a green plant. A green plant is a photoautotroph. It uses light to feed itself through photosynthesis. Contrary to the theme song in The Big Bang Theory, an autotroph will never drool. Nitrosomonas gains its sustenance by converting a high-energy chemical, namely ammonium, to a somewhat lower energy chemical called nitrite. It absorbs some of the energy released in that reaction, and that's what it lives off of. The two other bacteria genera, Nitrobacter and Nitrospira, take nitrite and convert it to nitrate, and they gain energy to live from that reaction. So it's a totally different way of meeting microbes' needs, but they both are available to take up oxygen in a BOD's test. Here's a microphotograph of two of those species, two of those genera. Nitrous stromonas is on the left and Nitrobacter is on the right. Notice it's a fairly complicated cell, but it has no mouth, it has nor any anus. It has more in common with a potted plant than a paramecium. Nitrous stromonas does not care for direct sunlight and does not need the presence of of carbon, because where carbon is found, heterotrophs are going to be really abundant. It's going to have a hard time finding its way. So both of these bacteria genera have an arsenal of organelles to help them alter the chemicals that they take in and absorb as much of the energy from that conversion as they can. They shut down when the water temperature gets below 50 degrees Fahrenheit or 10 degrees centigrade, or the alkalinity gets low, and they are destroyed by solvents such as acetone. In a word, these guys are finicky. So step one of nitrification, it's a bacterially mediated process. The first step is the slower of the two, and therefore it's called rate limiting. And basically what that means is that if Nitrous stromonas isn't playing on the playground, nobody else is going to get to play. So Nitrous stromonas takes in the ammonium, they convert that to nitrite, and they gain some energy from that. And then once they have it converted to nitrite, Nitrobacter nitrospira can take that and gain energy from that reaction and leave it with nitrate, NO3, as the ending chemical of that. When hydrogen ions are generated, such as in step one, as shown here, they have an opportunity to create acidic type conditions. And that's unfortunate because Nitrous stromonas and Nitrobacter nitrospira do not want to be in low pH. They want to have high alkalinity where they can do their work unfettered. So when hydrogen ions, it tends to lower the pH, and we don't want that. Okay. So the keys to treating high strength wastewaters, well, there's two of it. We need to design high strength wastewater treatment systems based on both the hydraulic load, how much water is there, and the organic load. So the design load is the sum of the hydraulic and the organic materials. Now, you're pretty used to using the first half. We need to add the second part. It's going to take some math that you may not be used to doing, but I'm sure you can do it. So let's get into determining these organic loads. So the organic load is found to in pounds or kilograms, but they're determined mathematically using some pretty interesting mathematics. So let's see if you can follow what I'm trying to say here. I have a problem for you, and you may have seen this problem before. We have a sewage flow of 450 gallons per day for a facility, and the soil in the area has an absorption rate of 0.4 gallons per square foot per day. What I'd like you to do is tell me what the size is of that soil absorption system. And I think you're going to see that what most of you would do is take 450 gallons per day and divide it by 0.4 gallons per day per square foot. And you'd come up with an answer of 1,125 square foot. Well, that's the correct answer, but I've got one last question for you. When did you get so good at algebra? Because that's what you use to get that answer. Here we have GPD above and below a divider, and it cancels each other, and it's now no longer in the equation. And also we had a number 0.4 gallons per day per square foot, so square foot was below, and now when we divided that, it comes up to the top. Both of those things are algebra, and we're going to use it even more as we go further in this topic. So I have a confession to make. As I went through college, I realized I no longer had it to memorize equations or formulas. Just stopped doing it. Instead, I followed the units to get the answer that was being asked for. To do that for you here today, I first need to develop a conversion factor. So that conversion factor involves more precise numbers, less rounding than we're used to seeing, but everyone focuses on the numbers, but I'm going to ask you to focus on the units because they are really the most important thing. So most of us say it's 454 grams in a pound, but actually it's more 453.6, 1,000 milligrams in a gram, and 3.785 liters in a gallon. We're going to take all three of those and come up with a conversion factor. And that conversion factor is a really small number. It's 0 followed by a decimal point and then 5 additional zeros, 834. But the units are liter pounds divided by gallons milligram. And you'll find that that is sort of the key. We also call that 8.34 times 10 to the minus 6, which tells you to move the decimal point 6 spaces to get the original number. So we want to calculate pounds per day of CBOD. And we can do that using this equation. The flow, which is gallons per day, times the CBOD concentration in milligrams per liter, totally different measuring units, but they are going to be canceled out eventually anyway. And then we have our conversion factor. So if we have a restaurant with 500 gallons per day and the CBOD is 800 milligrams per liter, which is not an outrageously high number, you can get much higher than that in numerous high strength waste applications. When we have our conversion factor, what we're going to find is that first of all, there's gallons above and below a divider line. So poof, don't worry about them, they're gone. It's gone to 1. The milligrams above and below, they're gone too. And now liter, it's the opposite. You know, the first one, it's below the divider, but in the conversion factor, it is above. And so we wind up with all of that, multiplying these things, the units that we're going to wind up with is pound per day. So we'll use that for an example restaurant. Say it's a 500 gallon per day restaurant, pretty small, but let's just do that. 800 milligrams CBOD, and our conversion factor, and that particular facility is going to generate 3.32 pounds per day of CBOD. Now let's compare that with a residence. A residence with the same flow and a more appropriate 140 milligrams per liter CBOD in residentials, you'll wind up with 0.58 pounds per day. So is it any wonder that facilities that have 7 times the loading of a residence would have trouble when we try to design it using a residential code and the data that's in there? Now, Arizona, hasn't jumped into this, but a lot of states are in the same position. There's only a handful of state on-site codes that refer to organic loading, and those ones are sort of leading the way, but there's certainly room for others to come aboard and start thinking about the math loadings and not just the hydraulic loadings. Some research that was done in the state of Florida while I was the contract manager for the University of Florida. We started a multi-year research project on food service establishments. And we basically had 15 different food service establishments, all within the Gainesville, Florida area. That's where the University of Florida is located. And the university basically did this work, and I'm just reporting on it to you. Full service restaurants, self-service restaurants and both of those are many hours a day, basically breakfast, lunch, and dinner. But there are self-service restaurants that take less hours than that might just do breakfast and lunch or lunch and dinner. A drive-in, bar, cocktail lounge, 2 grocery stores, and 3 convenience stores were all studied in depth during this project. So samples were collected really quite a number of years ago. It was 1997 to 1999, and they were able to look at all 15 of these food service establishments and get multiple samples from them. We wound up having to take composite samples because grab samples were as variable as you're going to see in this data. The grab samples were just unmanageable. So the data from that, we had 109 data points of CBOD, and the mean was 374 milligrams per liter, but it ranged all the way from 53, a low, all the way up to over 1,000. We also recognized that there were different groupings within each of these different parameters. So there were low high strength waste, sort of like a jumbo shrimp, I guess, medium high strength waste, and high strength waste. And these were valuable information to get from sampling actual facilities so that we could build some additional efforts into determining the long-term acceptance rate. And we'll get into that in just a little bit. With FOG, there was 122 samples, TSS 128, and they all had different means, standard deviations, ranges, etc. But a lot of data was collected and was used to categorize all 3 parameters in terms of their particular strengths. So most facilities had a wide range of CBOD per site. There were 2, site 13 and site 6, and these were charbroiled hamburger places, and you would expect them to have pretty high CBOD. We found out that the owner of the restaurant, in an effort to keep their systems from failing, was pouring in chlorine to the systems regularly, and so this data is of no value for that particular parameter in here. The rest of them, some stay in low and go a little bit into the medium strength. These are things like the bars and some of the other establishments. And then a lot of them are quite wide between medium and high strength. And some of them are consistently high strength. When it came to TSS, there was even more variability. In some cases, the site had TSS that was in all 3 categories, depending upon when it was sampled. And so there are a lot of TSS and the systems that were using the chlorine addition, that really didn't affect TSS. That was as variable as the other ones. And then FOG just goes really all over the place, and it gets quite strong in certain types of establishments. So we have these 3 categories, and we can basically create a synthetic wastewater and try to reach these targets. And they never really could get to the target. They were always a little bit underneath it, because as you're mixing the witch's brew together, you have the mixer itself would become coated with sticky components, and it wouldn't get into the sample. It was basically collected by the stirrers, etc. No wastewater was included in these synthetic wastewaters. They were pathogen free. They used spam, dextrose, which is a type of sugar, vegetable oil, and dog food in various recipes to make each type. consistently under target because of the problems with the mixing. So native Alaskans have 17 different words to describe snow and ice because they see it all the time. Well, Floridians have multiple words to describe sand because we see it all the time. So we have sand, fine sand, loamy sand. We also have levels of saturation. We certainly don't have the kind of depths to water table that you have there in Arizona. So we have a 2 foot, that would be a standard. 1 foot would be for repair. 3 wastewater strengths, the low, medium, and high. And each were done in triplicate. So there are 3 columns for each of these combinations. So there were a total of 76 columns put together, including 4 tap water dose columns to act as a control. These were dosed twice a day over time to develop a response to the wastewater that was being put on the top of the surface. So we had a 6-inch limestone aggregate, and then either a soil was, all soils with profiles were 42 inches, and they were whatever the particular soil was that is very common in the Gainesville area. The airports allowed oxygen to get into the soil, and also the water T set where the water table was in each of these. So you have a 2 foot unsaturated zone and a 1 foot unsaturated zone. And so they were then run for multiple days, and as the effluent was then collected in the container at the end of the day and discarded, and then leaving the cup open for whatever's happening the next day. So soils have names. In our case, the most popular soils were the Candler series, the Millhopper series, and each of them has a different color and texture of soil with depth. So the Candler City, all 42 inches, were yellow medium sand. In Millhopper, a different color, etc. And these were put in a 12-inch pipe, many feet long, and basically filled by hand. We also have a lot of places in Florida that don't have suitable soils, and so what they do is they basically take off the O horizon and add fill to those, and they could use either acetula or Candler as fill in places that have unsuitable soils. So this is one rack of lysimeters that were set up to determine the long-term acceptance rates, and these are all getting low. These numbers of columns going from 1 to 24 are there's a control, but there's also a low strength wastewater that it's put in at the ones closest to you have 2 foot unsaturated zones. The ones on the other side have only a foot of unsaturated zone. And so these were dosed repeatedly over time. During this study, 3 graduate students got their MS engineering degrees doing this project. Brian Matachek is in the left-hand photograph, and he was one of the main people who got really excited about this and did an excellent job. Now, a column failed when the last dose was visible above the aggregate just prior to the next time a dose was coming in. So you knew when it says the column was about to fail, and you were given early warning when you looked to drain that the night before and there was no water in there. It didn't fully drain out of the column, means it's backing up and it's going to fail very quickly. So this shows the answers for high strength and medium strength. The low strength that I showed you before actually did not fail, while these were failing consistently in shorter time periods. So the systems in the middle that are basically, they have an outer circle and then an inner circle, those are all 1 foot unsaturated zones. So it sort of makes a letter T made out of that particular thing, that particular situation of the 1 foot unsaturated soil. And you had Candler in yellow, Millhopper was in black crosshatch, Pomona was in a bluish color, and Pomona with Candler fill was in a green color. And so you see failures occurring, some very quickly, like within 20 days, so less than 3 weeks, and systems fail, but some took quite a few days, up to 112 days of being addition of this high strength waste or medium strength waste on a recurring basis. And so we had failures, we wanted failures, so that was a good thing. But when it happened and how it happened was sort of the key to understanding what was going on. So the hydraulic loading was not responsible for the drain field failure. The organic loading and the biomat formation was what really made it happen. And so reduced soil permeability just basically didn't let it get through, and the organic loading failure thresholds exists. And if you wind up organically loading above that threshold, that's when that drain field is very likely to fail. And so what this research taught us was a couple of things. For sandy soils, which is most of what Florida is, the loading rates greater than 0.024 to 0.0043 pounds per square foot per day, what I taught you earlier, how to measure the organic loading. And we took the CBOD and the TSS values combined. Those were the ones that resulted in ponding failure. So this is basically the threshold you want to stay under. Below a critical loading level of 0.014, the soil columns did not pond. And over time, you can get more CBOD and TSS transferred across the soil surface if you keep below that threshold in terms of mass loading of your BOD TSS. So I didn't mention fog because fog is the kryptonite when it comes to getting failures. And so it's very important that when you're dealing with food service establishments, that you design and maintain gravity grease interceptors to protect that drain field. So the design concept, what it is we're trying to achieve, we want to take wastewater with a high level of fog and food solids and effectively retain as much of those solids and fog as we possibly can. We want to release a treatable wastewater into the next downstream component of the system. And in the photographs here, we see a very common situation is basically wait staff, basically creating a lot of problems for that wastewater system. Instead of taking these food scraps and putting them in the garbage, they're trying to send them down the garbage disposal, where they're going to increase the pounds of BOD that the system has to treat. And also, I very cautiously talked about the next downstream component, because what I'm talking about, grease interceptors, is equally valid whether we're talking about a restaurant row in a large city or whether we're talking about a single restaurant on a on-site system. They both need to have functioning grease interceptors to protect what comes after the restaurant discharges. So the design concept for a grease interceptor, it has to accept the grease-laden liquid from a food service establishment, hold on to it, and let that contain liquid cool. The lighter than water fraction of that wastewater will rise to form an upper layer. And the upper layer can be very, very thick in a grease interceptor. The solids, though, settle on the bottom in a sludge layer, maybe 6 inches thick. So flotation and solid settlings must occur under calm conditions. The technical term would be laminar flow, and not a lot of turbulence. And what we want to do is allow a cooled, clarified liquid to exit the interceptor by hydraulic displacement. So hydraulic displacement, simply, if 1 gallon comes in, 1 gallon goes out. Now, if 10 gallons go in one 15-second period, it's not going to escape in 15 seconds. It's going to take a lot longer to get out than it got in because of friction and gravity and all those things that are going to get us all eventually. So we have 3 different types of grease interceptor, and depending upon what the code requires, you may only have to do one or others, but I really like to use all 3 of them. Hydromechanicals are basically used inside the food service establishment itself and can collect wastewater and get it solidified prior to going outdoors to the next tank. And automatic actually is a good option depending upon the kind of restaurant and what kind of fats, oils, and grease they are using in their cooking. What this does is it heats up the material, and there is basically a windshield wiper type thing that dips into the liquid, comes out and gets squeegeed off and gets held into this this white container on the side. And what that'll do is it'll get the grease while it's still yellow grease, and much more good price for recycling yellow grease as opposed to brown grease, which you might get from a gravity grease interceptor. There was a time not too long ago where people were just trying to get rid of this stuff anywhere they could, and now they basically have this under lock and key because it is valuable. Even the brown grease can be used for making diesel, biodiesel. And the yellow grease, ladies, hold your hands over your ears. That's used in cosmetics. So lipstick, base, all that stuff. So these 3 things are all options, but I'm going to focus on the gravity grease interceptor because that's the most common one. And there are 3 ways to get good performance out of a gravity grease interceptor. The first, I call them the 3 T's because each one of these begins with the letter T. So the first T is time, because we have to cool this. We have to get it to a point where fats begin to congeal and come out of a liquid form. And that's a function of the total capacity and the flow path that goes through these grease interceptors. So we use baffles and compartments to prevent short circuiting. We also use commercial grade filtration to make sure that the solids will start to congeal on there. And if that happens, then the liquid oils will begin to accumulate on there as well because they have a lot in common. Temperature, that's a function of what you start out with, the hot water setting, detention time, and surface area, because we do need to cool these things quite considerably to start to get the fats, oils, and grease to come out of suspension. And this T should have like a circle and a cross through it because we don't want any turbulence. We want a material to settle based on its specific gravity. So anything that has specific gravity less than 1 is going to float, and that's going to be most of the fog. And the any solid material like that person who was trying to get all the bones and such through the garbage disposal, that's going to be in the sludge. So temperature, the first T. A commercial dishwasher will discharge 170 degrees Fahrenheit water. If they switch to a chemical sanitizer, it allows them to lower the water temperature to about 130 degrees Fahrenheit. So big deal, right? No, it really is a big deal because animal fats will start to come out of suspension right around 100 degrees Fahrenheit. So you're getting it much closer to that value by using a chemical sanitizer. So it's very significant. Some have used airlines to strip out the temperature, but when they do that, they make a turbulent mess out of things, and I don't recommend doing that. So melting points of various lipids are shown on this slide, and I'm reminded of the old statement by Mark Twain that said, all generalizations are false, including this one. And so I'm telling you that these are the melting points, but it doesn't happen exactly at 84 degrees for pig fat. It is over like a 5-degree period, and it just gets more and more solid as you get cooler and cooler. Olive oil won't come out of suspension until it's 43 degrees. So unless you're living in Alaska, you're not going to get olive oil to come out. But the other points is that the depends upon the species of animal. It also depends upon where in the body those fats are taken from. So there is a, with sheep, it's 104 degrees for belly fat, but there's a different melting point for what they call leaf lard, which is around the kidney area. And also for cattle, it's 90 degrees with corn fed, but it's a lower number with grass fed. And that's why grass-fed beef is so, popular. It melts in your mouth, and so that's why. Turbulence, fog, floats, suspended solid sink, and the way that you can instantly tell if the tank you're looking at is a grease interceptor or a septic tank, look at the outlet and inlet pipes. They're going to be much deeper close to the bottom of the tank than they would be in a standard septic tank. So here's an example of a concrete baffled tank, and it has inlet, outlet, and then it has the sample pit. That's basically will be used in cities where they will take a sample from every restaurant on Restaurant Row, and then when the lift station needs to be replaced, they're going to come around and take a mandatory collection from each of the restaurants, and they'll all be saying, "Oh, it's the Mexican. No, it's the Chinese. It's this, it's that." They all pay for their errors of omission and commission, and so they wind up having to replace that at hundreds of thousands of dollars, and everybody puts in their fair share. So grease interceptors for septic systems are located outside of the food preparation area. And the distance from the building is a factor. If it's too close, the water will remain hot and emulsified fat and oil and grease get through the interceptor. If it's too far away, the sewer line clogs before the discharge reaches the tank, and you get these lovely types of photographs. And so it's showing you also what'll happen is that the animal fat will congeal first, but because they are very chemically similar, the vegetable oils will then collect on that same material. So vegetable oils are somewhat water soluble. They'll only be retained if there's some animal fat for them to coat. So where we put this grease interceptor, parking lot's a good choice, loading dock, under decks if they have hinged access. A 30 to 60 day service frequency is what I recommend. If you have to go out every week to service a grease interceptor, it's way too small. If more frequent service is needed, it's too small. And if you can stand it in the tank on solid grease, it's been too long without service, and I have done that. So clearly, some people are not really fixated on how long it's been since their grease trap has been pumped, and as long as they can, not get yelled at, they will stop trying to do it. So, in order to get more details about what's going on with these grease interceptors, I have to move over into mechanical engineering and really talk about thermodynamics. So there's heat transfer modes in which, and this diagram shows a camper holding a pan of water over a fire, and heat is being transferred in 3 different ways. Convection, shown inside the pan, causes the fluid, and the fluid could be either a liquid or gas. They're both considered fluids. If they move close to a hot surface, they get to transfer the heat to that. Conduction is heat transmitted through solids or second material, and this person is about to drop their pan because that handle is heating up through that. And then the third way, radiation, heat transmitted as electromagnetic waves, definitely very important in cooking of food and microwaves, all that stuff. But all of these ways that are using something to be heated up in reverse will be how something gets cooled. So I want you to have, it's not quite lunchtime where you are now, but imagine that you're going to lunch and you're going to get a steaming bowl of soup. I know it's hot there. I know you probably wouldn't want that, but go with me on this. And so it's delicious. You can smell it. You'd like to eat it, but it's literally fogging up your glasses. You can't get close to it. Of these 3 things, which of them in reverse would you use to try to get a taste of this delicious soup? I think you'll agree that what you would do just out of reflex is you would blow on the surface of that soup, and that's convection. And so that is exactly what we want to encourage in our use of grease interceptors, is we want them to cool very effectively, and that way we can congeal the fats, oils, and grease and get them out. And what I recommend doing is putting an air vent, a low vent, on the outlet side of the last grease interceptor that you have in series, and let air move across the surface of that tank and go out through the roof vent. As that happens, it's going to take the heat with it, and it's going to be a lot more effective in your preference of how that grease interceptor functions. And the density of air is on in our favor here. The hotter the air gets, the less dense it gets. So hot air rises, cold air sinks, and so you're able to get air preferentially out of the grease interceptors and up the pipe to the roof, very nicely with this situation. Another thing to think about is preventing short circuiting, and this is an idea that comes from Leon Holt, who was retired from Cary, North Carolina, and he calls it, I call it a double-barreled grease interceptor. Basically, in a one-pipe type system, you're hoping that as water moves from inlet to outlet, that it's going to basically take the whole center of the tank with it. And that's not going to happen. It's going to be basically something a little bit wider than 8 to 12 inches that's going to move through there. So by using what he calls a distributed inlet, he creates multiple flow paths going through that tank. And so the one thing that's not accurate in here is that the bottoms of all those pipes should be much, much lower, because that's where it's coming off of. Basically, we have a release, and the hot material will come to the surface. It'll be close to where the air is flowing through to get it cooler, and then go into the other side. And then at the bottom here, he has a distributed outlet that is taking it out. and I have an idea to improve that a little bit. So I would like to put in multiple effluent filters on the outlets of these tanks. And what they do is they train the restaurant owners to get service before they have a major problem. And these are two in series, and they basically, you're looking at the top of them. These are large commercial filters. They have multiple plates on them that can collect. And you see the white here, that's actually milk fat. So if milk fat is starting to come out, you've got it pretty darn cool, and that's a good thing. Beneath them, there is pipes down to the floor of the tank, because these would get incredibly heavy over time. And you couldn't just cantilever them out into the liquid and hope they would stay there. They would crack open that pipe, and everything would be on the floor. So you put a toilet flange on the bottom, and then you put a length of pipe up to the base of these, and let it fill up over time, and you can, change them out on a nice regular basis. So what happens if you leave it alone is you get an emergency call from the restaurant that, hey, we need to have our grease interceptors pumped. And yes, you certainly do. But it didn't get so bad. So it kind of trains them to not put this off, not wait to the last minute to get something done. And what really is impressive is that the vegetable oil is right in there. It is mixed in with that fat. So the oil is being taken out as well. So you're getting both of them. So facility, how to figure out what is necessary for them. Typical operating hours, those are going to be the places where you have peak flow. What is the 4 square foot of that restaurant that the owner knows the most about? It's basically the 4 square foot around the cash register. They keep an eagle eye on that. So they should be able to tell you how many meals they served today, how many meals did they serve yesterday, etc. And you can check your sizing by using that information. The menu itself doesn't really impact grease interceptor sizing. I think it's a red herring to start worrying about stuff like that. It's just now there is something though. Self-service salad bar creates a fog nightmare, and I'm as guilty of this as anybody. If I am served a salad at my seat in the restaurant and they bring me a little cup of dressing, I very happily put that cup of dressing on my salad. I spread it all over. I eat it. It's delicious. I love it. But if I'm at a self-serve salad bar, basically I'll take a scoop and put that on my salad, but then I'll think, well, I really could use another scoop on there. And you wind up really having a lot of fog in the wastewater because you're overusing that dressing. Better plate scraping is very important, and use of disposable paper gives the best improvement in effluent. So we are famous in this arena of telling people, well, congratulations, here's your septic tank. Here's what you can't do now. And so I really don't want to take that negative tack with people. What I'd much rather do is ask them, okay, what's your plans for a deep fat fryer, and how much money you're going to make, because it's going to cost a lot more to design it, and it's going to require more frequent maintenance. Is this something that works for you? Rather than just say, you can't do it because you were silly enough to use an on-site system. Now, self-service soft drink and ice cream drippings are very high in BOD. They should be eliminated as much as possible. And the ice machine drippings and cold water thaw sends many gallons of water to the system unnecessarily. So try to stop that from happening. When you're in the field, you may be able to troubleshoot effluent characteristics pretty easily. If you put your gauntleted hand in the grease interceptor at the outlet and you can't hold it in there, right there, it's telling you that that's too small. It's short circuiting. There's some kind of problem with this grease interceptor. A solution might be using a chemical rinse, a distributed inlet, commercial grade filtration, or more tanks if you possibly can. If the pH is low, that means that there's excessive chemical use in the facility, and basically the person who is selling them chemicals to use with their system is basically overloading them because he wants to take a trip to Hawaii, and basically he wants you to pay for it. Final tips and tricks. If there's excessive fog, even at 100 degrees Fahrenheit, you can change the menu from vegetable oil to vegetable shortening. Now, vegetable shortening includes lard, which is an animal fat. So it's not something that a person who's a vegetarian or a vegan would be willing to make that kind of change. But depending upon the facility, they may say, yeah, I'd be more than happy to go to vegetable shortening. And that would mean that you would get solids out of solution at a much better temperature. So once you begin to solidify at higher temperatures, it allows the vegetable oils to coat that fat material. And my last tip is make sure you service all your tanks just before Mother's Day. I think, oh, final thoughts. Okay, high strength waste system designers can work in either direction or both. They can pre-treat the effluent using mechanical means or an alternative drain field product, etc., or they can increase the size of the soil absorption system. That would work on the square footage of the equation, or they could do both. And if they are successful, they will have long-lasting high-strength waste systems. Remember the 3 T's of grease interceptors: time, temperature, and no turbulence. And the high-strength waste solutions depends on what parameter is high and how far above normal is it. And final warning, none of this makes any sense if there's toxins mixed into these wastes. So toxins trump strength. And that's it. I can take any questions that you want to send my way.
All right, Kevin, I'm not seeing any questions coming in other than just a few. Oh yeah, we got one now from Ray. What's the most cost-effective method of treating high-strength waste?
Well, I'd say the most cost-effective, and it would be cost-effective in sort of a rural setting, would be a larger drain field size, because you're basically lowering the loading on each square foot of property just by using more square foot. So that is definitely an option. But what happens in areas where space is not available, or it's awfully pricey, then you start looking at alternative treatment methods and dropping that BOD, TSS, total nitrogen in the effluent before it reaches the soil surface.
Okay, what are some problems that can occur in septic systems for unmanned dump stations?
Unmanned dump stations?
Yes.
How much time do we have? Because there are dozens upon dozens of problems with that scenario. If it's, oh God, you would regret having something like that unmanned. Basically, there's going to be toxins. There's going to be high strength because of very little mixing water, and if no one's watching, I just don't know what kind of shenanigans people would pull.
Okay, how can RV wastewater be treated?
RV wastewater is definitely a high strength waste. It does have toxins in it as well. And what happens is that the owners of the RV, they don't want to smell the waste. So they put a lot of chemicals in there trying to control the waste, but it actually winds up making it less and less treatable. What I've found that works pretty well is basically taking the wastewater and not trying to treat it, you know, with anything at first, but basically set up multiple tanks. Maybe allow like a 7-day retention time and allow the off-gassing of that material before you then try to either treat it or dispose it into a large drain field if you have such a thing. If you have lots of space and can do that. And you'll find that the time that you gave that to off gas, the materials that are placed into these RV wastewaters to basically curb the odors are all what are called volatile organic compounds. And if given the opportunity, they will escape from the liquid into the gas and would be no longer around to affect the wastewater. But if you try to treat it right away, no chance. It's basically it's on life support, and the bacteria are just not able to do anything with it at that point.
Okay, are there any other questions that anyone has? Not seeing anything else.
Okay, good.
So I'd say if no one has any other questions, we can go ahead and wrap this up. I did have a question. Yes, we will post this recording on the ADQ website. It will probably take us 3 or 4 days to get that up. And then hopefully we'll see all of you at the July 26th meeting to go over the changes to the rule and upcoming redesign of the on-site program. All right, everybody, thank you for your time. Have a great day. Kevin, thank you very much. We appreciate your participation.
You're very welcome.